Our project is called flood forecasting. So we want to use citizen science to improve flood forecasting models. The CrowdWater project is a collection of hydrological data made by citizens, and we have the earliest data in February 2017. In this data, we have a lot of information about water quantity, water quality, like for example, the color of the river, of the water, about pollution, if there is plastic on the river and what kind of plastic and something like that. We have some stream information, like for example, the width of the river, and also a lot of images that citizens took of each station. The data that we want to use for our project, what is our project? We want to make use of this CrowdWater data to improve flood forecasting models in those stations, in those rivers that has not real gauging stations, real gauging data. And so we can help flood awareness. So the kind of data that we are going to use is the European Flood Awareness System, that is a pan-European domain. And the EFAS has a resolution, a spatial resolution of 5 by 5 kilometers. And it is an EPSG 3035 as a coordinate reference system, a Lambert azimuthal equal area coordinate reference system. And we have a temporary resolution of 6 hours. As you can see in the image, you can see the region of the EFAS domain. And then we have the CrowdWater data. We have a CSV file with 51 columns where we have a lot of different information, as I said before. So we have the day and the time in which the citizen scientists took the picture or the information. We have water level on virtual scale, as you can see in the image here in the right, and we are going to see this in detail later. Latitude, longitude of each station, and the route ID, that is the identification of each station. And then we have images. We have one image for each station in which we have the virtual scale, and multiple images after that without the virtual scale. So the first thing we did was cleaning the CrowdWater data. So we selected some relevant columns for a project, like for example, the virtual scale, latitude, longitude, day and time. We removed, there were a lot of rows with null or empty values, so we removed them. And also we removed the station that had only one observation, because we wanted at least 2 observations for each station to have something to compare. Since the CrowdWater project is worldwide, we concentrated mostly on the EFAS region, and so we removed all the stations that were outside the EFAS region, so the pan-European domain. And then the last thing we did was transforming the values of the virtual scale. As we saw before, they were text like -1, +3, and so on, and we transformed them in numbers that we could actually use. We selected a number of usable stations, and we had, for example, 367 stations with 2 or more readings, but still 2 readings were too little for our project, so we decided to get at least 15 or more readings per station. So at the end, we had 50 stations in the EFAS region. So the problem with the virtual scale, when we selected the stations that we wanted to use, we needed to understand what the virtual scale means, because this is not actually what is the meaning of a +1 in this scale. And what is the meaning of the -2? Is it the bottom of the stream or not? We don't know that. We only know that the 0 is the level of the surface water. We had other problems, like for example, these virtual scales didn't mean the same thing across different locations. As you can see, this scale is bigger than this one. So a +1 here is different from a +1 there. Another problem that we had is sometimes in some stations, these virtual scales were really big, really not representative of the actual water level. So even if we had a water level variation here, the measure will always be almost zero because this +1 is too big to measure this variation. Or at least even if we imagine that the water level may reach level 7, it seems something like a little bit apocalyptic. So it's not really representative of what happens in this river. So we didn't have only the pictures with the virtual scale. There was only one picture with the virtual scale for each station. We had a lot of other pictures like this for each station in different days, in different times, but still understanding the water level variation, it's not easy only from the picture. We wanted to try to use those pictures, and so we concentrated more on the virtual scale, on the picture with the virtual scale. And we came up with different proposals. We checked machine learning to use with the pictures, but actually we don't have so many pictures, so it was difficult to apply. And then we read some interesting papers about forensic photogrammetry in which they estimated the height of the suspects from CCTV's frameworks. But still, it was not applicable to our project because the images were completely different from the ones that they used in forensic photogrammetry or as orthophotos, for example, transforming the pictures in something in which we can take pictures on, in which we can take measures on. So we stick to the third method, that is the manual estimation. So the four of us just looked at the first picture of the 50 stations that we chose at the beginning. And from some objects that we have in the background, we try to estimate manually the amount in centimeters of this step. So for example, this seems to be a solar panel that might be 2 meters. And so I go there and say, oh, well, a +1 might be 80 centimeters. That maybe is too big, but we have 4 values and we could also remove outliers, for example. The same thing in this picture there. So we can say that this pole is 2 meters and each step might be 6 centimeters and so on. So each one of us made this estimation for each of the 49 stations because one station has no virtual scale, so we couldn't actually use it. And we estimated the virtual scale height. As you can see, we have a lot of different values. Sometimes the values are really equal to each other. Sometimes they are really big or really small. So we had to choose some station and to remove them. So for example, we computed the mean of the 4 heights for each station. We already removed the station that had really different values. And so we got at the end only 38 stations and not 50. But still, the mean of the 4 values didn't seem to us so representative of the actual value of each step of the virtual scale. So we decided to compute another mean after removing the outlier for some stations. Like, for example, this station here, the 4th station, it has 3 really equal values and 1 outlier. So we removed that and computed the mean between those 3. Sometimes they were all 4 really similar, so we kept all 4. And we did this manually because each station was different. So this is a comparison between the 2 mean. We selected the red one, the one in which we removed the outliers. And then what we did was using those values to substitute the virtual scale that we had at the beginning. And this was really helpful. One, because we had something in the metric system. The other one is because we can compare different stations. For example, these two stations here. And that was a really big thing for us, because at the beginning we couldn't compare the stations because the virtual scales were different from station to station. So what we want to do now is creating a general equation by learning the parameters of this equation using real gauging data and some extra information that we are going to get to use this general equation with the parameters in stations where we have only the water level variation from CrowdWater. Because there are a lot of small rivers in which we do not have real gauging stations with real data. And in those stations, the flood forecasting model might not be so good. Using the CrowdWater data that are taken in the station might be more useful to get better flood forecasting models. So then the extra infos, the next thing that we did was computing the width for the station, for the bigger rivers, and we used simply Google Maps and we just computed it in this way. For the smaller rivers, we actually had the values in the CrowdWater CSV file. And and this is what we achieved so far. So we selected the CrowdWater stations. We converted the CrowdWater virtual values to standard metric in centimeters, and so we can compare the different stations. We computed the width of the river, and now what we want to do is using the digital elevation model of the regions in Europe to get the order of the river, the upstream area, the catchment, and then using different characteristics of the catchment, like the slope, the cross-section, like for example, saying that, let's say that the cross-section is trapezoidal, and so on. So, thank you.